hopefully that will help people who didn't catch us this morning, because it was some time ago, to see exactly what's happening. So the first thing I'm going to do is I'm going to whiz through some of these slides. So we look for patterns in the data, and the topic of this session is different ways that we can analyse the data to start to think about looking for fraud. So there's been a lot of questions about the Covid-19 virus. There's been a lot of concerns that the data has not been analysed properly. There's also been concerns the data has not been collected properly. And there's also been insinuations that governments are hiding the true number of cases that they actually have. So when we look at data science, we are interested in trying to understand better if the data is in some way fraudulent or not, and we can do some forensics to understand why that might be the case. Because when we start to look at data, we can analyse it in different ways. We can see what's happening, what will happen, and what people should do. And the main things we are concerned about with the COVID environment that we see at the moment is what will happen next. So I'm going to pop my way through these. And I'm going to talk a little bit about something called Benford's law. Now, Benford's law is quite interesting situation with data. What we see is we find that the number 1 appears more frequently at in the very first part of a data set than number 2, and number 2 appears more frequently at the start in the very first digit than number 3. I'll see if I can find a quick example just to show you. So this is the data set I wanted to show you. Sorry, I see a message. All right, keep trying to get in. Okay. All right, so we've got something here called the law of anomalous numbers. I'm going to put that into the chat window just so you can read it. And this was written by a gentleman called Mr. Benford, believe it or not. His name was Frank Benford. You can go and look at this. But what he said was we have got the situation, what he called anomalous numbers, where there's a strong tendency for bodies of numerical data to fall into categories. So you can work out the frequencies of the first digits in different orders from 1 to 10 and so on and so forth. So when we look at the list of countries by GDP, when we chart this data, we see that the number 1 appears most frequently, followed by number 2, followed by number 3. So we're looking at the position of the first number in the sequence. There's some evidence to show, and we will have a look at this, that we use Benford's law when we're doing forensics as part of a fraud detection process in data. So Benford's law proposes a distribution for the first digits of numbers in naturally occurring data. So government accounting and statistics are similar in nature to financial accounting. So, for example, in the European Union, there's a pressure to comply with the stability and growth criteria. So, like firms, governments might like to try to make their economic situation seem better than it is. In the same way with the COVID environment, there might be an inclination for governments to try and make their data appear comfortable or better than it is, partly because they don't want people to panic, but also there's a concern and an uncertainty about the future. People are worried what's going to happen next. So there's been plenty of reports about this. For example, the Eurostat's data was analysed and a Benford test was conducted to investigate the quality of macroeconomic data relevant to the deficit criteria reported to Eurostat. And so there was some analysis to found that some of the countries showed a greater deviation from Benford's law among the Euro states. Now, Benford's law, I should say, is not a silver bullet catch-all. It's a suggestion that something is funny or a bit dodgy about the data. And that's why we use it. It's one of a range of tools. It's not the only one. So we see this Benford's law appearing again and again. So people have applied it to the economic data in China and found something funny going on there. It doesn't mean there's anything funny going on. It just means it deviated from Benford's law. And we find that Benford's law occurs quite specifically in very many data sets that we see. So, for example, if you look at things like the GDP growth rate from 1991 to September 2012, you can see that there's a suggestion that the 0 occurred as the second digit 21 times, whereas we're expecting to see that, we're not expecting to see it appear quite so many times. And that's much higher than what Benford would calculate. That suggests that data has been rounded up to achieve a bigger leading digit. So 1 through 4 also appears more regularly than the law reckons, while 7 to 9 appears less. So what that means is that there's a potentially an incentive with some data sets and some of the economic data sets to round up the second digit that appears in the sequence. So if the number was something like 36.5 million, but it would be rounded up to 37. And that might be right, but you may want to report it as 37 million as opposed to 36.5 million. So these small, what looks like a small rounding, can actually point to something. Maybe there's an incentive for people to round up their data or to round up their currency. So it's also called the first digit law. And what it does do is it states that for many real-life sources of data, the leading digit is distributed in a specific non-uniform way. So according to this law, the first digit occurs about 31% of the time. That will be number 1. And number 2 will appear 18% of the time. And then we find that number diminishes, and then eventually poor number 9, it appears as the leading digit less than 5% of the time. And here's a quick history lesson for you. A gentleman in 1881 called Simon Newcomb, he picked up his statistics book of tables one day. I remember looking at these way back in university, but I suspect that many of you are just using computers to do that now. But we used to have books you had to look up, and you had to look them up just to get practice so you knew what was going on. So Newcomb noticed that when you opened the book, the figures, the statistics for 1 and 2 and 3, those pages were much more well used and well worn than the numbers for the later digits. And that led Newcomb to realise that actually, perhaps there is a pattern in naturally occurring numbers, where 1, 2 and 3, so on, appears more frequently as the leading digit than the later numbers. So he did a bit of an analysis on this, and I hope you can see, but in this table on the right-hand side, he went and analysed lots of numbers. He went and analysed things like the heights of buildings, and he analysed the population of cities, and he did all sorts of things like that. And what he found is that the number 1 appeared 30% of the time. So if this was a data set, number 1 would appear here. In this column, 30% of the time. Number 2 would appear in the green column 18% of the time, so on and so forth. So he found this pattern that was quite interestingly occurring in data. So Benford's law is, we've got a summary here, just as I've said, you can look this up in Wikipedia. The first digit leading appears as number 1 30% of the time, then it diminishes. So from theory to application, this is something that we look at when we start to look at data. Got Dr. Mark Negrini here. If you can, I suggest you look at his paper. He published a thesis noting that Benford's law could be used to detect fraud in data, in transactional data. He suggests that human choices are not random, and it suggested that invented numbers are not likely to follow Benford's law. So what he really was saying that is if somebody is fiddling their expenses, you won't see the pattern and the data appear as it is here. If somebody is fiddling the numbers, you might see 6, 7, 8 and 9 appear more frequently in this column than these numbers, these percentages would indicate. So you might see number 7 appearing 30% of the time. You may see number 8 appearing 17% of the time. So that tells you the numbers are not following a sort of almost a natural pattern that we see in a lot of real life data. As I say, it's not a magic bullet that fraud's been going on, but it does suggest that there may be something funny and it's worth another look. So Mark Negrini is an economist. If you can get the chance to look at his data and his papers, I recommend you do. So this Benford's law has been applied to lots of different things. It's been found to apply to people's bank transactions. So if you download your bank transaction next time or your expenses, maybe have a look and use Benford's law to see how your data appears. It can apply to journal entries, stock prices, expenses, so on and so forth. It does not apply to certain types of data, so telephone numbers, where it's a number but it's really nominal data, you won't find it there. People's heights, for example, you would not expect to see Benford's law appear there, because probably the leading digit for most people's height in centimetres is going to be 1. So it's for certain things there will be a natural limit and it won't apply. So it doesn't apply if there's a cap or a threshold being placed on the data set anywhere. And it doesn't apply for aggregated data. So for my expenses for my company, you might find that they follow Benford's law at the granular level, but if you summarize that data, it may not apply there. So aggregated data doesn't really tell you anything. The average, for example, has obscured the detail in the data. Also doesn't apply to very small data sets. So if your data has got less than 500 transactions, then you might find that the data doesn't appear. So the reason I'm mentioning this is when we start to look at the data for COVID, we can start to consider whether or not we could use it for Benford's law or not. So when we conduct an audit on data, we are checking for a few things. We are checking for Benford's law, which we just discussed. We're looking for outliers. Outliers are sometimes irrelevant, but sometimes they are the start of a new trend, and that's why we need to capture them. So social media companies are usually desperate to capture the outliers before they get caught out. So we're also interested to see how the data is acquired. Now for COVID, well, this is actually really interesting. Acquisition of the data is important. So we have seen with the UK that the way they collect data in the UK is actually going to be very difficult to compare, and there's a number of reasons for that. It's quite difficult to analyse it. So we have a difference between NHS Scotland and NHS for England and Wales. So the NHS Scotland figures are released very slightly earlier than the cut-off date for NHS England and Wales. So what we find as well is that the data, when it's collected, is not, although they release the figures every day, they don't collect the data every day. So for care homes, the figures for that are released on a Wednesday. Not all hospital trusts release their weekends data on a Monday. Some of them will do it too late on Monday to be included in the Monday count, or it will be released on Tuesday. So the timing of the cutoff is also important. We also need to think about how we can align some of those data sets. So what we need to do is think about how do we align that, because the Scottish data is Sorry, somebody's sending. Sorry, somebody keeps sending me messages. I'm going to have to get. So what we'll do is we will think about how we can collect the data and how we can acquire it. So we see straight away there are issues with the data. Now the care home data is interesting because what it does do is it can show us that there's straightaway discrepancies in the data, but it makes it difficult to compare. The care home data is really interesting because we've seen from some of the European data that the care home deaths account for between 15 and 50% of the overall deaths. So if we are not collecting data during the week, that is a care home or a community death, that means that the official figures for the UK that day are not the full story. They are missing out quite a large chunk of data, anything between anywhere between 15 to 50% on top of that. So what we have now is a situation where we're acquiring data and we find it difficult to align. And we're also put in a position where we are not sure how we can align the data, but we are also pretty sure it's not correct because we are not collecting all of it. So what we have is a strange situation where data acquisition is not accurate and it's not including all the deaths. And we're also in a position where the data is at different grains. Some of it is daily and some of it is weekly. And what we have to think about is how can we align all of that? Because the thing is, we seem in the UK anyway to be treating UK care home people as if they are in a hospice rather than a care home. And there is a difference between a care home and a hospice. A hospice is where people go because they're nearing the end of their life, usually because of an illness. Care homes are supposed to be about trying to provide extra support to people who cannot live at home. That does not mean that they are needing death in any way. It just means they need extra support. That could be mental health, for example, or it could be some sort of disability, which means they require extra care. It doesn't mean that they are waiting to die anywhere. So it makes me a bit cross that the care home data is being dismissed in this way. I think it's wrong. So when I look at that data, I think they are trying, I think they need to work harder to collect it. And I think the data acquisition process is due to the fact that they've not been testing as rigorously as they should have done, which comes down to due diligence. So data visualization can help you to audit your data, and we have got demo and Power BI. And we've also got Benford's law, outliers and missing data. So these are different ways that we can start to think about how we analyze and we audit our data. Data visualization is great because it means we can have the patterns of the data jump out at us. So if you bear with me, I know some of you missed this morning and I'm expecting that. I just wanted to show you this. This is called Patternicity versus Apatternicity. So our brains are very finely tuned to find patterns in the data that we need. So in the right hand side, I don't know if you've seen that, this picture is called the jurist, and you can go and look it up, but you can probably see that it's made up of sea fish. And it was supposed to be a comment about the legal system at the time. And then on the left hand side, we can see it looks to us as if there's a human face in there. And it's obviously just a cut in the rocks. But for us, our brains are so finely tuned to look for patterns in the data. That's what jumps out at us. So that's why data visualization can help us. So I just wanted to give you a quick example. This is from the OECD. The idea is that we have looked at the overall deficit surplus total as economic metric, and we see in that economic metric that the number one appears 28% of the time. And what we have here is we have got Benford's law. So Benford's prediction is that the number 1 would be the leading digit 30% of the time. So in the data for the overall deficit surplus total, we have got it appearing as 28%. So it's quite interesting, I think. We can start to see how the data actually matches or is very close to what Benford would predict it to be. And then when we visualize it, which is just basically done in Excel, you can see the pattern straight away. Benford predicted that the data would look like this in terms of 1, 2, 3, and so on and so forth, appearing as digits. And then we see the actual what happened in the blue bars, and we can see that as a line chart as well. They are quite close to one another. So before we move on to a demo, what we can see is that Benford's law is not the final word, but it's a great start for the curious, and it's something that if you've never seen it before, I recommend you go and have a look at it, use it and have a play with it next time you play with the data. The other thing to do is just keep doubting yourself when it comes to data. I think that's important. Doubt yourself and then keep proving everything. There has to be a degree of cynicism in all the data, and I think maybe that's why so many people find the actual COVID data so interesting. It feels like data science is being put on trial. The only time the general public come across lots of data like this is when we have an election, and we all know how predictable the election data usually is. We usually find that it's completely different, the result, from what the polls actually say. So it feels like data science is a little bit on trial as well. So we have to think as well about the repeatable principles in science too. So we have Occam's razor, and Occam's razor, as you may know, is usually we like to think that the simplest explanation is the right one. So I think when I deal with people, I find often they will confuse likelihood with possibility. So it's possible I could be sat here in a Santa suit presenting this, but it's not very likely. And when I speak to people about data, when I'm designing a data warehouse system, sometimes these edge cases will come up when people say, aha, it might work like this. And this one case is supposed to gazump the whole data warehouse. Then you have to say, yes, but is it actually likely that it will happen? And then at that point, the conversation becomes a bit different then. So it's quite interesting law, I think. So if you've never seen it before, I think you should have a look. So I'm just going to come out of this. I'm going to check to see if there's any other questions. So if you have a quick look in Teams is what I'm going to do. And if there's any questions, pop them in there. Right, so a lot of people have joined, a lot of people have left, which is kind of what we're expecting, I suppose. All right, okay, so I'm going to jump off of Teams. And then we'll have a quick look at the data in RStudio. So what I'd like to do is show you this data. And now, if you've never seen R before, I recommend that you do play with it. R, I think, is a fantastic way of expressing statistics. I think it's something that's really, really useful. And I think a lot of people are getting excited about it because it helps you to analyse data. You'll be glad to know that there is a library in R that conducts Benford analysis for you. And what it does do is its main purpose of this particular data set is to find out exactly where the data set deviates from Benford's law and to identify any suspicious data that might need further verification. So it gives you some sample data sets. So one of the sample data sets it gives you is corporate payment. And this is just a very sample data set to give you a quick demo of what it looks like. Okay. So now if I give you the head of corporate data, corporate payment rather, what that's going to do is it's going to give you a small visibility of what the data looks like. So this is just some made up transactional data. We can see the vendor number, we've got the date, then we've got the invoice number, and then we've got the amount. And what Benford's law is going to do is it's going to make predictions about the number of times that 1, 2, 3, 4, 5, so on and so forth appears in this column here. It will propose that the number 1 will appear in the first digit 30% of the time, number 2 will appear 18% of the time, so on and so forth. Okay, so that gives us just a little visibility of what the data looks like. So we've got a head function in R, we also have a tail function as well. And the tail function is just going to give us the bottom 6 rows of the data. And what it's going to do is going to predict how many times number 1 is the leading digit. Okay, so it's got this nice function. And what it's going to do is it's going to check the amount, this column here, against Benford's law. And it's going to see if it works or not. So it's not, it looks like it's not done anything, but what we can do is plot that data. So when we plot the data, what we can see here is the distribution. Now, Benford's law would suggest or predict that the number of times that these digits appear, we've actually, in this case, now normally you just look at the first leading digits, but what this has done is, by default, it's started to look at 2 leading digits, and that's why we see 2 leading digits here. And what that does is it will give us a plan, really, to see if we can check the first 2 leading digits. So what's nice about this example is you can see in the data, it kind of follows Benford's law, so you can see it's quite close for most of them, most of the digits. But what it does do, and this is an interesting point, is you can probably see that around number 50, we've got a big spike there. So for the curious data scientist, we would want to understand why that is. And what we would then do is go back and look at these transactions, because what it might tell us that is that for the vast majority of the data, everything appears okay. But maybe, just maybe, the data was manipulated where the green part is. So that would give us something to investigate. So we can start to do some other charts as well. This gives us some more detail about the data. But what we could do is we could run Benford's analysis, Benford's law, against some of the COVID data that we see. So what I'm going to do is I'm going to show you the data first of all, and then we'll start to have a bit of a play with some of this. So you can see the end result. I've ran this against the first 2 digits of the COVID example. And the interesting thing is that the data mainly follows Benford's law. But the interesting thing is we've got these really interesting spikes, which I'm going to highlight in green. So these numbers, for some reason, Benford's law is not being followed. So as a data scientist, I would want to go in and analyse that further so I can understand a bit better what's going on. But what I'd like to do is show you the data, and then we can have a look at how we got there. Okay, so what I'm going to do is go back and I will show you what the data set looks like. I'm just going to dig out my data here. Now this data has been obtained from Kaggle. Right, so what I'm going to do is show you where we got the data from. I'm just going to pause my screen while I dig it out. So I've got the Kaggle data set here, which I think I had. Oh yeah, here it is. So you can see, sorry, the Teams control is in my way. That's better. So here's the Kaggle data set here. I hope you can see it all right. I'm just going to leave that there in case somebody wants to take a note of that and play around with the data themselves. All right, so sorry about that. I have two dogs and one of them's crying at the back door to be let out, so I've just had to go and let him out. So here's the data set here, and we can see there's some quite interesting columns. We've got the ISO code, which is the country code, so this is Aruba, and we can see the country code here in green, and we've got the location, which is the country here. And you can see the country name just there. And we've got the date, so not all of the data looks like it's present for Aruba. So we can see that there's a jump from the 13th of March through to the 20th, and then we see some of the dates are missing. So that is interesting because we can start to look at the missing data as well. Okay, so then we've got the columns here. And you can see you've got the dates there. And you've got cases, you've got the new cases, total deaths, new deaths, so on and so forth. And there's a lot of information here. The nice thing is that we've got such a nice variety of data, and I will see if I can find the, oops, I can't see it. It doesn't matter too much. I thought I could find the cargo data set, but I'm sure you can find that yourself. So what I'm going to do is we'll have a look at that data in Power BI. So we can see the data here in Power BI. So the data appears, we start to see it appear, but it's given us the data for 2019 as well. So we can start to filter some of that data. So when we look at our options, we could take this data and turn it into a table. So when I right click on the data, we can start to see the data appearing as a table. We have got it for various countries here. And then I could just copy this and then put that in as a table just so we can see the data a bit more clearly. So I'm going to copy the visual, and I'm just going to put it here. So we've got the paste button over here, and then I'm going to have that as a table just so we can see it better. So this data is just the new cases. So we've got the months here. We start to see some months appearing in China in December. And then we start to move into January. The rest of the world is only seeing some new cases. But obviously we see a big jump where China is. So it's interesting because this one is new cases. I'm just going to rename this so we can remember that that is the new cases one. So we've got the data there. So this new cases data, we can see quite clearly it appears in here, but I'm more interested to see it by date. So I'm just going to zoom down and have a look at it here. Now I'm going to remove quarter because I don't think that really tells us anything. So then I'm going to drill down again. So we can start to see these spikes appearing. They are organized by date. So I'm just going to remove date from there because it looks a bit odd. And I'm going to add in date in axis. And then I'm going to set it to be date rather than hierarchy. So now what we start to see is we can't see the data very well. I'm just going to get rid of that table just now. Now the thing is, when we visualize data that appears in a timeline format, doing it like that is too hard to see. So what we can do is start to add it in as a line chart, and hopefully that will make it clearer to see. Doing it as a line chart is more intuitive from the data visualization perspective. So this is new cases that we are looking at. So we see here this huge spike in 15,000 new cases on the 13th of February, then it starts to fall away. So what we could do is try and add in new deaths as well. And we can see if that would apply in here. We've got new cases. I don't know if new case deaths will let us do anything. Okay, we start to see big spikes appearing again. So that's because we're looking at deaths here. But that's not very serious subject, so we can start to look at new cases. So what we could do is, there's been lots of questions over whether this data is fraudulent or not. So with the new cases data, we could put that into Power BI and see how it works. We can see China has got a big spike here. But if we start to exclude China, then that gives us an idea of what the other countries look like. So I'm going to just change location. I'm going to just select all, but then I'm going to remove that and look for China. And then I'm going to look for the United States. And I'm also going to look for the United Kingdom. So by adding in these three, I'll make them different colours actually. So I'm going to go to data axis, and then we've got data colours here. China and the United Kingdom are too hard to distinguish, so I'm going to make China just red just now. Make United Kingdom, leave that as purple, and I will put this one as a blue colour. Let's see if that makes it look better. All right. So what we can start to see here is the new cases and new deaths by location. So we see that the number of new cases a day, China here we've got, and we've got more information in the tooltip. So for China, we've got new deaths is in there as well. Oh yeah, that's why the tooltip's down here. I don't know if you can see that, but the new cases appear in the values, but we've also got the tooltip showing you the new deaths as well. So I can remove that, and then it may make it easier to understand. So now we've got 10th of April, we can see that United States are confirming over 33,000 new cases that day, and United Kingdom 4,344, and China are reporting hardly any. So it's interesting because I think the line chart really helps us to see patterns in the data. So the interesting thing is that we can use that same CSV sheet and we can put it into Power BI. And we can actually put our R in here as well. I'm going to go back to our studio. Our studio is here. So that data that I showed you in Power BI is the exact same data that I've assigned in R, and it's going to be assigned to this variable here, which is called confirmed COVID. Now, one of the powerful things about R, I think, is that R can assign anything to a variable. That could be a model, it could be a data set, it could be a result, it could be a file. So the power of R, I think the reason it's taken off so much is because it has the ability to assign anything to a variable, and it makes the code quite readable. So I'm just going to remove the China cases one. We won't look at that, we don't have time. But what we've got here is when I type in confirmed COVID down here, that's going to give us the first 6 rows of the data that we saw in the CSV file. So we saw this before. We've got Aruba in here. Then we've got total new cases. Now this is a cumulative figure, so that's why it increases. And then we've got new cases appear here. And then we can see new cases per million. So what we could do is we could summarize the data for each of those columns, and we can do this in R. This will give us the min, max, the median, and the interquartile figures for each of the columns where it's specified a number. So number of new deaths, we see the maximum new deaths here, and then we've got mean here as well. We just looked at new cases. So when we look at new cases, we can see maximum 35,000 plus in one day, and the median says 1, and then we've got mean in there. So we've got our data and we could analyse that further. But the other thing is that we'd like to do is try and do the same Benford analysis on the number of new cases a day as we did do for the data previously. So we ran this result previously, and for me it's quite interesting to understand why we see these quite regular distributions, why those appear in that frequency. So we can go back and start to look at that data in Power BI to understand why that data starts to appear. We can try and replicate that. What this data is, what these formula are doing here is it's working out the Benford's law and comparing that with our actual data set. And this is the results it gives us. And then it prints out the results and it will plot that information too. So now we can see our results. If I just do that line here, we can start to see things like the 5 largest deviation. So we can see the largest deviations at which points they appear. They appear at 10, 20, 30, so on and so forth. So that to me looks strange. And there may be a very good reason for it, but it seems that the biggest deviations in the data appear when there's another new 10. I'm not sure why that is, but that's when the biggest difference appears from what we expect to see in Benford's law. I'm really curious why that is. I might have to go back and dig through the data and have a good look. But what I like about R is it gives us lots of information just with one simple command. So let's go back and have a look at the data for new cases in Power BI. We're just going to add in new cases. So we can see the number of new cases totaling more than 2 million. And that is what we see when we start to look at the headlines. That kind of matches. We knew the last week that we topped 2 million new cases of COVID overall. So what we have is new cases here, and we've got the date. So I want to understand better why that, or if that spike appears. So I'm just going to add in the date, and I'm not going to add it in as the hierarchy. I'm just going to add it in as the date as an individual. So what we'd want to do is understand when the data starts with 10, 20, that kind of thing, why the data looks like that. You can see here the number of cases starting to spike and increase. And we can quite easily turn this into a table. So to do that, I could copy the visual, but we've got this other thing in here, which is something that's a really quite a cool feature in Power BI. We've got the ability to analyse the data and find where the distribution is different. So let's try that and see what Power BI actually does. It may not find anything, but let's have a look. So it's going to have a quick whiz through our data. So for new cases, it's comparing the proportion. So in this example, hasn't really found anything, although it has found some spikes in the data. We can see 13th of February, where a lot of new cases on that day. Not sure why. And we start to see where it deviates from where we might expect. So there's a lot of new cases appearing here, even though it's in. Even though it's expecting it to be here. So it'd be interesting, because it doesn't mean there's actually an increase in the number of cases. It might just mean there's an increase in the number of cases being reported. Okay, so what we can do is have a look through some of these other analyses as well. So total tests per 1,000, and then the number of total tests. So it does it for every single column. If I wanted, what I could do is add this one to the chart. So I'm just going to click on that. And what that will do is it should add it to my Power BI workbook. So, and we can see that just here. I'll just delete that one. So it's quite nice. I think it's almost like they're starting to do artificial intelligence on business intelligence, helping you to create charts simply by typing in what you want. So I hope that gives some insights. Just to summarise, before I see if there's any questions. Power BI. So to summarise, Benford's law, it's not the final word, but it's a great start for the curious. So we have to get back through the data and keep analysing it. I'd love, as the next step, what I'd want to do is go back and look at the data that appears with the 1, 0, 2, 0, that kind of thing, and try and understand why that data appears to spike at certain points. It just simply could be a matter of reporting, and there's more cases reported every 10 days or something like that, and that's why it spikes. But I'd have to go in and I would have to try and understand what the case is. So very simply, sometimes the simplest result is the right one. As data people, it can be quite hard to remember that. We're always looking for more and more information. But it can be quite hard to drop things and move on. Now, there's one last thing I wanted to show you while it's in my head. And I'm sorry, I forgot to show you this. When we go to RStudio, I can drop this code. And I can drop that into Power BI. So I'm just going to copy that, go to Power BI, click here, and start a new chart. I'm going to add in R. Then I'm going to type or click on the data that I would like to use. So I want new cases and I want date. And what I would like as well, could add in location, for example. There's a code. So what I could do now is add in my R codes down here. So I'm just going to take that out. We don't need that. All I want to do is really plot that data. So let's see how that works. So it can display the visual. I'm going to have a quick look. All right, so it says it can't find something, so it can't find out. I need to change that. So it says data set, I think data set. Like that. New cases, I'll try that. Yep, there we go. So it looks a bit messy, but what I should have done really is stretch that, and then I'll run it again. That's better. So what this gives us is the same data that we saw in RStudio. So again, we see these really funny spikes appearing when the data starts with a 1, 0, 2, 0, so on and so forth. I'd be really interested to find that is. We see the same pattern appearing every 10 days over here, so that looks quite odd, I think. And we can see the chi-square difference. So I'm interested to see more information about why that is that way. When we go back to RStudio, we can see the results in more detail. RStudio over here. So we can see the probability over here for new cases. Okay, so I'm just going to double check in Teams to see if there's any questions. Otherwise, we can start to wrap it up there. And here we go. So I can see a question. Benford's law is just about digit. Can you do anything similar for text? I believe you can, and it is called, I forgot the name of it. I haven't. I did look at that. You'll have to bear with me. It's a German name. I'm sorry, it's forgotten. I'm just having a quick look in OneDrive. I did something like this for a customer. Yeah, it's called the first letter law. So it's like Benford's law for digits. And I've forgotten the name of the man that did it. Yeah, if you look up FLL, that's the first letter law. And that should be, you should be able to Google around for that. If you are, I'm just trying to think of that name. I want to say Liechtenstein, but I don't think it's that. So I'm sorry, that other thing is gone. Something I presented a while ago, and it is gone, I'm sorry. Right. Any other questions? No. Right, thank you very much. Thank you for joining the session as well. Thank you, Ashraf. With that, I think we've only got a few minutes left, so I will pause there unless there's any other questions. Thank you.